we've already pretty much covered the difference between experimental and theoretical probability, but I just wanted to take one day to kind of hammer it home a little bit more. Okay, so experimental probability is based on what has already happened. Theoretical probability is based on what could possibly happen. Okay, so one is sort of looking to the past, if you will, and the other one's sort of looking to the future. Okay, so experimental probability based on what has actually happened requires some kind of a data or experiments or tests to be able to work with experimental probability. Okay, so it's the number of times that an event occurred divided by the total number of times that the trial was repeated. So this problem right here, we've actually done this before earlier in your note packet, but they asked a bunch of adults if they've flown in an airliner and got this data. So the probability that a randomly selected adult has flown on a commercial airline would be, well, 710 people said that they had flown on it, compared to a total of 855 people. Right? So my experimental probability, 710 divided by 855, is 0.830 or 83%, 83.0%, excuse me. You got to keep the zero if you're rounding to a tenth. Okay, so that is the idea of experimental probability. Now, theoretical probability is based on what could possibly happen. So you look at the number of ways that it's possible for event A to occur divided by the total number of ways that the results could work out. So this guy right here is roulette. So you've got kind of an example of what a roulette wheel looks like here. Depending on what type of roulette you play, like there's a European version versus an American version. Sometimes it looks a little bit different, but for our purposes, this will work for us. Okay. So the idea of how roulette works is that basically this whole wheel spins, and when you drop, somebody drops a little ball into it and it bounces around a little bit and it lands in one of these little slots. Okay. So if you've ever seen any movie that took place in a casino ever, you've probably seen roulette. All right. So here's our wheel. Okay, you plan to bet on the number 13 on the next spin of the wheel. So somewhere in here, there is a 13, and that is the number that you are planning to bet on. Okay, so we want to know what is the probability of losing. Okay, so 38 different slots on this, so you don't have to pull it from the picture, but there's 38 different slots. There's a 0, a double 0, and the numbers 1 through 36. And again, depending on if you're looking at the American or the European version, it's a little bit different, but that's the general idea. So in this case, the probability of losing, okay, there's 38 slots altogether, and only one of them is the number of 13. So your probability of losing is there's 37 possible outcomes where you lose divided by the 38 total outcomes available. So you have a 97.4% chance of losing any given time that you spin the roulette wheel. Okay, so you can sort of see the difference, right? We didn't actually play roulette. We didn't actually look at any data about what happened with roulette being played. We just looked at, in theory, what could happen on this wheel. Okay, so big point here, right? The point of theoretical probability is to give an estimate of what could actually happen. Okay. The more times you repeat an experiment, the closer the experimental probability gets to the theoretical probability. So what that's saying is that if you just spin the roulette wheel once and you bet on 13, you might get lucky, right? You might get lucky and you might get it. And that would totally defy what our percentage of losing was, right? If you could do it twice, the likelihood that you would get it twice in a row, that's lower, right? So the idea is that if you were to actually play roulette and you were to collect data on what you got for every spin, as you spin and spin and spin and spin and you get up into the hundreds of trials and the thousands of trials, you're going to get closer and closer and closer to what this actual probability is. Okay? So taken to an extreme, experimental probability should be the same as theoretical probability, again, taken to the extreme. So if you're looking at it with like lots and lots and lots and lots of cases, maybe not perfectly, but it should be pretty close. Okay. And that is kind of what the point of these probabilities are. Okay, so we're going to look at these ones, decide if it's theoretical or experimental, and then answer the problem. So this first guy here, adults are randomly selected for a poll and asked if they're in favor of the death penalty. we had 319 responses in favor, 133 against, and 39 who have no opinion. So based on that, we're going to estimate the probability that a random selected adult is for the death penalty. So right away, I know this is experimental probability because they have actual data from actual people. Okay, so this is going to be an experimental probability. And, right, the number of people who said they were for the death penalty was 319 compared to the total number of people. Let's see. So we had 319 plus the 133 plus 39. So there was a total of 491 people. So our experimental probability, 319 divided by 491, is 0.64, well, okay, 0.6496. So this 6 would make that 9 round up, which would make that 4 round up. So it would actually be 0.650 or 65.0%. That's our experimental probability. All right, next one. Find the probability that if a couple has 3 children, they will have exactly 2 boys. We're going to assume that boys and girls are equally likely and that the gender of one sibling does not influence the gender of the other. Okay, so this would be a theoretical probability. We're not going out and looking at how many people have actually had babies, right? We're just strictly looking at it and saying, okay, well, based on what we know about how babies work. Okay, so this one is a theoretical probability. Okay, so let's take a look at this. So first of all, we're going to have to figure out the number of ways to get what we want, right, versus the total number of possibilities. So figuring out the ways to get what we want, the exactly 2 boys, how I'm going to kind of think about this is I'm going to kind of think about it like a word problem, right? 2 boys and a girl. So you know how like we rearranged like the letters of the word Mississippi? I'm going to think about it that way, right? I've got 3 letters, but 2 of them are the same thing. So there's 3 different ways for that to happen, right? So the ways to get what we want, right, would be 3 factorial over 2 factorial. Okay. All right, versus the total possibility. Well, the total possibility, you've got 3 kids with 2 options for each one, so that's 8. And then 3 divided by 8 is 0.375 or 37.5%. And there we go. Now, worth noting about this problem, right? So when we look at this one, you know how it says in here, assume the genders are equally likely and that one sibling does not affect the gender of the other? Okay, that's because when we look at experimental probability, right? Theoretically, every time a child is born, it should be a 50-50 shot boy versus girl, right? But based on experimental probability of having observed many, many, many births over the years, we actually see that having a girl is slightly more common than having a boy. Like I think it's something like the percentages are like 51% girls and 49% boys. So it's close, but like, you know, we've gone to the extreme with the number of births, right? We've had plenty of births to record data on, and we do find that it's a little bit skewed. It's not quite 50-50. Okay. And then additionally, gender of siblings does seem to have an impact. Okay. And it's obviously, this is really complicated. They don't really know how it all works. But it does seem like the gender of one sibling does seem to have an impact on the gender of the other. So that's why those kind of caveats were there, was because theoretically, we observe a 50% chance of a boy versus a girl, but experimentally, we kind of view something else. Okay, last problem. This one, if a year is selected at random, find the probability that Thanksgiving Day will be on a Wednesday or on a Thursday. Okay, so is this experimental or is it theoretical? Well, I mean, you could sort of make an argument for both, but I guess it's sort of more theoretical, right? Because we're going off of what we know about this holiday, right? Thanksgiving Day is the 3rd Thursday in November, right? So is it ever on a Wednesday? Never, right? That's theoretical. I mean, you could also argue experimental because it never has been on a Wednesday, right? So there is a 0% chance of it being on a Wednesday and a 100% chance of it being on a Thursday, right? Because that's how Thanksgiving Day works. Okay, so that is the difference between experimental and theoretical probability. They're both useful in different instances, and it's a useful thing to have both of them. It's just that, for experimental probability, you have to do a little bit more legwork than theoretical probability.